The question is, discuss the differentiability of a complex valued function fz is equal to 1 by z. Here fz is a complex valued function, and for any complex valued function fz is equal to u plus iv to be differentiable in a domain D, two conditions must hold. Number 1, ux is equal to vy and uy is equal to minus vx at all the points in the domain D, and the second is ux, uy, vx and vy, these partial derivative must be continuous at all the points in the domain D. Here ux means the partial derivative of u with respect to x, and uy means the partial derivative of u with respect to y, and in the question our domain D is the whole complex plane, and we know that the complex plane consists of the real axis, that is x-axis, and the imaginary axis, and their point of intersection is denoted by z is equal to 0, that is origin, and normally we denote the complex plane by capital C. Here in this question we will divide the whole complex plane into two parts. One is origin, that is z is equal to 0, and the second part is all the points of the complex plane other than origin, and we will discuss these two conditions in these two parts one by one. For this we will need the real and imaginary part of the given function. So let us separate out the real and imaginary part of fz. Fz is equal to 1 by z, z is x plus iy, so it will become 1 upon x plus iy. For separating real and imaginary part, we will have to multiply and divide this by complex conjugate of x plus iy, that is x minus iy. So it will become x minus iy upon x square plus y square, or it also can be written as x upon x square plus y square minus iy upon x square plus y square. Clearly its real part is x upon x square plus y square, and imaginary part is minus y upon x square plus y square. Let us denote the real part by u and imaginary part by v. So u will be equal to x upon x square plus y square, and imaginary part is v is equal to minus y upon x square plus y square. Now we will differentiate u and v partially with respect to x and y. The partial differentiation of u with respect to x is equal to uxy is equal to y square minus x square upon x square plus y square whole square, and the partial differentiation of v with respect to x, that is vx, is equal to 2xy upon x square plus y square whole square. Similarly, the partial differentiation of u with respect to y, that is uy, is equal to minus 2xy upon x square plus y square whole square, and partial differentiation of v with respect to y, that is vy, is equal to y square minus x square upon x square plus y square whole square. Now clearly we can say that at any point other than origin, ux is equal to vy and uy is equal to minus vx. So at any point other than origin, the first condition is satisfied, that is ux is equal to vy and uy is equal to minus vx. Now we will check the second condition, that is the continuity of ux, uy, vx and vy. Here ux, uy, vx and vy, these are all rational functions, and their denominator become 0 only at origin. So at any point other than origin, their denominator is not equal to 0, means these are all finite. So we can say that at any point other than origin, ux, uy and vx and vy, these are all continuous. So except at origin, these two conditions are satisfied. So we can say that fz is differentiable at every point other than origin. Now we will check out these two conditions at origin, and first we will check at origin, the condition number second, that is the continuity of ux, uy, vx and vy, and first we will take ux. So let us check out the continuity of ux at origin. Here ux is equal to y square minus x square upon x square plus y square whole square. Ux is the function of x, y, two variables. So for checking the continuity of ux at origin, we will convert this function into polar form, and in converting into polar form, we will put x is equal to r cos theta and y is equal to r sin theta. So ux becomes cos square theta minus sin square theta upon r square. Now if taking limits r tends to 0, ux becomes finite, then this function ux will be continuous at origin. If it will become infinite, then it will be discontinuous at origin. So taking limit r tends to 0, we will get ux is equal to cos square theta minus sin square theta upon 0, that is infinity, because cos square theta minus sin square theta is finite. So ux is discontinuous at origin. So second condition is not satisfied at origin. So we can say that this function fz is not differentiable at origin. So the result is the given function is differentiable everywhere except at origin.